Going to be discussing gas expansions and heating problems, and what we need to be able to do is to calculate heat, work, delta U and delta H for a variety of different conditions. We need to watch out for words in our problems like reversible or irreversible, a free expansion versus a non-free expansion. The adjectives isothermal, isobaric, isochoric, and adiabatic are all important. And then we've got to watch out, are we talking about an ideal gas or are we talking about a real gas? Because that makes a difference when calculating the work involved in a gas expansion. So here is a set of problems for gas expansions. In this case, we are going to be looking at isothermal gas expansions. And we've got a sample of ideal gas that's initially at 5 atmospheres and 1 liter pressure, or 1 liter volume, and 298 kelvins. We're being asked to derive the equations we need to calculate Q, W, delta U, and delta H when the gas is expanded isothermally to 10 liters using these different paths. What I want to point out, for isothermal gas expansions involving an ideal gas, the internal energy depends only on temperature, as does the enthalpy. So if your gas expansion is carried out isothermally, then delta U and delta H are constants. So in every part of this problem, A, B, C, and D, delta U equals delta H, which equals 0. Okay? And that's for ideal gas, isothermal conditions. Always true. Okay, so you definitely want to watch out for this combination of words in your problem because it makes calculating half the problem totally easy. So what we really need to focus on are calculating heat and work. And in this first part, we have an irreversible gas expansion. I'm going to go ahead and draw the indicator diagram for this problem. So here's going to be 5 ATMs. So this is pressure in ATMs, and this will be the volume in liters. So here's 1 liter, and here's 10 liters. Let's see, we'll make this 1 ATM down here, and then here's half an ATM. So what happens in this problem? The gas is initially here, and then the pressure suddenly drops down to half an ATM. And then what happens is the gas is expanded, and then it stops expanding once it reaches 10 liters. Okay, so what we need to do is to calculate the work done in this problem. We need to calculate that area. And so in this case, work is going to be equal to minus the external pressure times the change in volume. Write it like that. So we've got the external pressure in this case is 0.5 ATMs. We have a change in volume that is 9 liters. And then what I'm going to do is convert that to joules. And so this is the conversion factor between joules and liter atmospheres. So I'm getting 456, negative 456 joules. That's the work done when the system expands from 1 liter to 10 liters. How to calculate the heat? We can use the first law, rearranging. Since delta U is 0, heat is just minus the work plus 456 joules. What's happening in this problem? The gas is doing work on the surroundings. It's losing energy. Ordinarily, that would cause its temperature to drop. However, because it's in contact with the surroundings and the temperature is constant, what happens is heat will flow from the surroundings into the system. So the system loses energy via work, and then it gains that energy back as heat. And as a consequence of that, the temperature does not change. It's an isothermal process. For part B, we are being asked to do a two-step gas expansion. So let me draw an indicator diagram illustrating what's happening in this problem. So again, we've got our five atmospheres, 1 liter initially. At some point, so the pressure is going to drop down to 1 liter or to 1 atmosphere, and then the gas is going to expand for a little while, and then at some point the pressure is going to drop again down to 0.5 atmospheres, and then it's going to expand the rest of the way to 10 liters. What I want to point out, because this is an isothermal process, all of these 3 points here, they lie along the same isotherm. Although what we want to calculate for the work, we want to calculate this area. The reason we need to know about the isotherm is because they haven't told us what that intermediate volume is. We have to figure that out. We can figure that out using Boyle's law, right, which tells us that, I'm just going to say P1 and we know P2 here is 1 atmosphere, but we need to figure out that second volume. So we'll say P2 V2. Solving for that unknown volume, so we've got 5 liters, 5 atmospheres over 1 ATM, and then that's times the volume of 1 liter. So it's 5 liters in this case. So now we know the second volume, and that allows us to do the calculations of work. So we can calculate the work for this rectangle here, and then we can calculate the work for that rectangle. So work is going to be a sum of the two. It's going to be minus 1 ATM. That's the external pressure for this first expansion. The change in the volume is not 9 liters now. The change in the volume is 4 liters, right? You're going from 1 liter to 5 liters. And then I'm going to be adding to that a work term for the second expansion where it's 0.5 ATMs for the external pressure. And then we're going from 5 liters to 10 liters. So there it's a difference of 5. And then we're going to be multiplying that whole thing by 101.3 joules per liter ATM. That's the conversion factor that we need. So I'm getting minus 658 joules for that work. And again, because it's isothermal, when we go to calculate Q, we just get plus 658 joules. What I want to point out, so we have, for this two-step process, it's a work of minus 658. Previously, it was minus 456. So we see that the gas did more work during the two-step expansion compared to the one-step expansion. Okay. Next, let's do the free gas expansion. So in that case, what that means is that the external pressure equals 0. And so what we're going to find then, of course, is that the work is equal to 0, and then the heat is going to be equal to 0. right? Because we already know that delta U and delta H are equal to 0 for this problem because it's an ideal gas expanding isothermally. In addition to that, the work is 0, and then of course if the work is 0, then the heat's 0. So that's what we get for the free expansion. In part D, what we're going to be doing is now the reversible gas expansion, where the gas is in equilibrium all throughout the expansion, which means that it's going to follow the isotherm. So the system is going to follow the isotherm down. And so what we need to do is to calculate the area beneath this curve. And that's given by a different formula for the work. It's for an isothermal gas expansion involving an ideal gas. It's nRT natural log of Vf over Vi, initial and final volumes. We're going to need to determine the number of moles of gas. And at either of the points, it's N is going to be equal to PV over RT. And so we can calculate that very quickly. So we'll take 5 ATMs. That's 1 liter divided by 0.0821 liter ATMs moles Kelvin. And then the temperature is 298 K. I'm getting 0.204 moles for that. So that can go right here. Then we'll use the other version of the gas constant, 8.314. That's joules per mole Kelvin. Take that times the temperature, 298 Kelvin, times the natural log of the final volume, 10 liters, divided by the initial volume, 1 liter. And that's going to give us our work. I'm getting minus 1,164 joules. So that's the largest magnitude of work that we've gotten, and indeed that's the largest magnitude of work that's possible for this gas to expand from this initial point to that final point. Like before, we're going to get Q equals to plus 1164 for this isothermal gas expansion, right? The heat lost as work is gained, the energy lost as work is gained back via heat. Well, in the next series of problems, what we're going to do is calculate Q, W, delta U, and delta H for heating up a gas. Now, when you heat the gas, the temperature is going to change, and in this case it changes from 300 to 500 Kelvin. So delta U and delta H are not 0 in this case. So for part A, all right, we're considering an ideal monoatomic gas, and the process is isochoric. Well, when it's isochoric, that means that the change in the volume is 0. Therefore, the work is going to be 0. Delta U is going to be, for an ideal gas, it's going to be the number of moles times the constant volume heat capacity times delta T. So this is for an ideal gas. And then the delta H is going to be in CPM delta T. Also, that's restricted to the ideal gas. Finally, because it's isochoric, that means that the heat is going to be equal to delta U. So I'll also add to this isochoric conditions. We make that identification for constant volume. Okay, so we can set these calculations up. We've got 2.5 moles. Let me define, before we get into that, let's define the heat capacities. So for a monatomic ideal gas, CVM is 3/2 RT, and CP, which is equal to CVM plus R, will be equal to 5/2 RT. So here's the number of moles. Then we're going to have 3/2 times 8.314 joules per mole Kelvin. And then we've got the temperature difference. In this case, it's 200 Kelvin. We'll go ahead and get that number. And then delta H, rather than repeating everything for delta H, what we can do is just say that delta H is going to be 5/3 delta U. And the reason I'm doing that is because CP is 5/2, CV is 3/2. And so if you multiply delta U by the ratio of 5/3, it gives you delta H. So I'm getting 6.24 kilojoules. Oh, I wrote it in the wrong place. 6.24 kilojoules. And then I'm going to multiply that by 5/3. That is 10.4 kilojoules. Okay, so for isochoric heating, work is 0 and Q equals delta U. For ideal gas, you calculate CV like this and CP like that. This is for a monoatomic ideal gas. Let's do the isobaric diatomic gas. Okay, so for the isobaric case, the work is not equal to 0. We're going to calculate delta U. This time, because there's rotational degrees of freedom, the heat capacity is going to be different. So it's going to be, instead, for this diatom, it's going to be 5/2 NR times delta T to give us the U. And then delta H is going to be, let's see, I think it's going to be 7/5 delta U in this case. So just plugging in the numbers. We'll get that value, and then we'll get the other one. So I'm getting 10.4 kilojoules here, and 14.5 kilojoules for delta H. What about the heat? For isobaric conditions, heat equals delta H. Not delta U. So now that we know heat to get the work, we'll take delta U minus the heat, and so we get about minus 4 kilojoules. Close enough. For part C, we're dealing with a polyatomic, again isochoric. So what we'll get is that now, in this case, the looking at this formula here for the internal energy for methane, D equals 6, and so we're going to have 3 nRT, and then for H it's going to be 4 nRT. So when we want to calculate delta U, it's going to be 3 times 2.5 times 8.314 joules per mole Kelvin. This has units of moles. And then the delta T is going to be 200 Kelvin. So that's going to get us our answer there. And then we'll do the same thing now. It'll be 4/3 times delta U to give us delta H. How to calculate heat? It's isochoric. So under isochoric conditions, Q equals delta U. And then to get work, we're going to do, work equals 0 for isochoric conditions. So let's get the number real quick. So I'm getting 12.5 kilojoules for my delta U, and 16.6 kilojoules for my delta H. And so that's all we get for this problem. In the last problem, where we're again dealing with methane, we are told that it's ideal, but then we're given that the heat capacity has a temperature dependence. This is a bit of a contradiction in terms. I sometimes call this the Idealish gas problem, because they want you to use some features of the ideal gas but not others. So in principle, the ideal gas has no temperature dependence to its heat capacity, but in this case they do want us to consider the temperature dependent heat capacity. So when you go to calculate delta H, for example, for this part, now you'll take the integral of n/CPm dt. You have to evaluate that integral specifically, and so it'll be number of moles on the outside, and then you're integrating this this function. I'm going to call this CPm. I'm just going to call it A plus B times T, where A is 18 and B is 0.06. When you do the integration, you'll get A times TF minus TI plus B over 2 TF squared minus TI squared. And then so you have to now evaluate that. That's a bit more detail than I wanted to go into here, but I'll let you work that as an exercise. So that's how you would do the delta H calculation. Because it's isobaric, it's also going to be equal to Q. To do the delta U calculation, you need to do the same thing, but using the constant volume heat capacity. not the constant pressure heat capacity. And so what you would do, you would use this result that CPM is equal to CVM plus R for an ideal gas, and so you would rearrange this. You would then need to integrate this function. Okay, so it's like just adding a minus R to this expression here. So it's not that complicated, but it is a little detailed. Once you've done that, in order to get the work, what you would do would be to take work equals delta U minus the value of Q. And that would give you the value of the work. So I will leave the numerical details up to you guys to work through, but this is the structure that you would follow for these calculations. Well, with that, I'm going to go ahead and stop this video here, and we'll pick up with thermochemistry in the next one.